Let's use some basic derivative rules. So here are the derivative rules we have so far in our first derivative section that we can use as shortcuts without using the limit definition of the derivative at all. So we know that I have a b here. This is just a stand-in for any like number on its own. So like in this first example, -8 is just like its own thing. The derivative of any constant number is 0. The derivative of any straight line is its slope. So if you have 2x, its derivative is 2. If you have 10x, its derivative is 10, and so on. And then the one that we're going to use by far the most often and for most stuff is the power rule, which will be the derivative of x to any number. Sometimes that number is a nice positive integer, sometimes it's a fraction or it's negative, but this rule always works. The derivative will come out to old exponent times x to the 1 less exponent. All right, so we also have these two rules listed below here, which aren't really like for specific functions, but they're telling us if you have two things added together or subtracted, you can add or subtract as the case may be their derivatives. So for example, in this first function that will differentiate, I'm going to have derivative rule plus derivative rule plus derivative rule plus derivative rule, like we can add them together as separate projects. And then we can also carry down constant multiples. So if you have some number times a function that calls for, let's say, the power rule, then that number is just multiplying on that power rule derivative. Notice that this is different from the constant rule above. This is for when a constant is like its own function, such as the -8. This is talking about when you have like a number times a formula, right? So in the second example, we're talking about the times 3. All right, let's do this first example here. We're given the function x to the 5th plus x squared plus 5x minus 8, and we're asked to compute its derivative using these derivative rules and not the limit definition. All right, so first notice that they're being added or subtracted. So this rule says you can just add and subtract separate derivative rules. So these are 4 separate projects. All right, we'll do x to the 5th first. The structure of this fits the x to the n rule, which is the power rule. So its derivative will be bring the exponent down, so we'll have 5, and then x to the 5 minus 1, which is 4. So this is 5x to the 4 plus, for x squared, this also fits the power rule. So if we use nx to the n minus 1, here the n is 2, so we'll have 2x to the 1 power. X to the 1 power is just x, so you don't actually have to write that exponent in. I just want to make it match the rule for this first example. 5x, I would say, fits in the mx category. It's a straight line, so its derivative is just the slope number, which is 5. And then we'll do minus the derivative of 8, and 8 on its own without multiplying anything fits in this category here, so its derivative is 0. We could leave it there, or if we want to simplify, we could say 5x to the 4th plus 2x plus 5 and leave out all the extra stuff. All right, let's do the next example. Here we have 3x to the 4th minus 9x plus pi. And again, we want to compute its derivative, meaning differentiate it, without using the limit definition. Because we have subtraction here and addition, we can use this rule to say, all right, 3 separate projects, I'll just add their answers. 3x to the 4th, I'm going to have 3 times the power rule for x to the 4th. X to the 4th fits in here, so I'll have 4x cubed. And then I'll subtract the derivative of 9x. 9x is a straight line with slope 9, so its derivative is just the 9. And then the pi is there to kind of freak us out, right? So x is the actual input variable of this function. So this plus pi is sort of the same as this -8 at the end. It's just a constant number, even though it's kind of a gross number. So its derivative is just 0. And again, I'll take an extra line here. I want to clean up especially the 3 times 4 to be 12. And I can leave out that plus 0. So I have 12x cubed minus 9 as my answer for this derivative. All right, let's get to some harder examples that involve some exponent rules. So this third function, we have square root of x plus 1 over x plus 1 over x squared. Believe it or not, all three of these derivatives will be using the power rule, even though none of them as it is right now actually looks like x to a power. So using exponent rules, we can turn each of these into a different form. So it's x to a power. Then we can use that power rule the way that we want to because we don't really have any other options. All right, so first thing is the square root. So the square root of x, by definition, is x to the 1/2 power. And then if you had like the cube root of x, like we'll have in this next example, this is x to the 1/3 power. So the square root and the 1/2 power are the same thing. Okay. And remember, I'm not differentiating in this moment. I'm just reformatting my function so that I can differentiate. All right, next one up is 1 over x. We have an exponent rule rather that says x to a negative power is 1 over x to that power. And typically we're using this rule in the opposite direction where it's like to compute a negative exponent, we format it like this so we can do something with it. But here we're going to use it the other way. And say, all right, if I see 1 over x to the 1 power, that would be x to the negative 1. And then I'm going to use the same rule for this one. If I have 1 over x squared, that's the same as x to the negative 2 power. So I haven't taken anyone's derivative yet, but I've now reformatted all three parts of my function so that the power rule applies to them. And these are more awkward numbers than we had in the first two examples in our power rule, so we're just going to be extra careful about differentiating. So for this first one, it'll be 1/2 x to the whatever a half minus 1 is. That's 1 over 2 minus 2 over 2, so that's negative 1 over 2. All right, so that's 1/2 x to the negative 1/2. The next one will be negative 1x to the negative 1 minus 1 is negative 2. And then finally, we'll add the power rule for x to the negative 2. So I'll have negative 2x, and then the new exponent is negative 2 minus 1, which is negative 3. For this one, you could leave your answer just like this. I would leave it like this unless the directions, told me to simplify it or write it a certain way, or if I needed to plug a number into it. So here's an optional version of it. We could kind of undo all of these exponent rules, right? So x to the negative 1/2 is 1 over x to the 1/2, which would be 1 over root x. Here we have plus and negative. I could turn into subtraction. X to the negative 2 gives me 1 over x squared. Just reformatting using the same exponent rule. And then finally here, plus a negative 2 could be minus 2. And then x to the negative 3 is really 1 over x cubed. So this is also an acceptable version of a final answer. And I would say if we needed to plug a number into this, right, if they asked for f prime of 1, I would have to plug in 1 for all these x's, and I think it would be easier from this form than from the original form that we got. All right, let's do one more example in this video. Again, we want to find the derivative. We have the cube root of x plus 2 over x cubed minus 9 over root x. And just like in that last example, I can kind of tell that all of these could be a power rule problem, but none of them are actually just x to a power. So I'm going to have this like reformatting step first, and then I'll do the power rule for all of them. All right, so square root of x is x to the 1/2. Cube root of x is x to the 1/3. I'll write it underneath this time since I have some space. Here I have 2 over x cubed. I'm going to see that as 2 times 1 over x cubed, which is 2 times x to the negative 3 power using this rule. And then 9 over root x is 9 times 1 over root x, which is 9 times 1 over x to the 1/2 power, which is 9x to the negative 1/2 overall. And I'm going all the way to this step because I need it to be x raised to a number to use the power rule. So I have to kind of keep going with equivalent versions until I hit this. All right, now each of these I can apply the power rule to, and these will have multiples, the 2 and the 9, that the previous example didn't have. All right, so for the derivative of x to the 1/3, that'll be 1/3 x to the, I'm going to have 1/3 minus 1, doing scratch work, so I get this number right. It's 1/3 minus 3/3, that's negative 2/3. And then I'll have plus 2 times the power rule for x to the negative 3. That's negative 3x to the negative 4. Minus 9 times the derivative rule for x to the negative 1/2. Negative 1/2 minus 1 is our new exponent. That'll be negative 3/2. And again, I could leave it this way. Since I have so many numbers multiplied, I'm going to take an extra step to at least reformat that. But I'll leave this in the fraction negative exponent way. So this is one version of a final answer. Or if you wanted to go a little bit farther, this x to the negative 4 could be a denominator of x to the 4th and so on, for all three of these terms.